nature-inspired design rules. And with that brief introduction, although I can go on to say a lot, that he has graduated 30 students and that he has been instrumental in developing many ECRs, many other academics that are even part of today's talk. But to keep it short and to look forward to hearing his talk, I'll gladly and warmly welcome Professor Price to share with us his new insights on the program plan that he's been discussing and to benefit the DSM community. Thank you, Professor Price. Floor is yours.
Thanks, Saurav. That's a very kind introduction. And yeah, it's been a real pleasure. I'm glad that we were able to attract you to come here and work in the UK. Thanks everyone, and thanks to to Alan and to the network for the invitation. Let me just share my screen and go into the presentation. So can everyone see that?
Yeah.
Yeah. Okay. Brilliant. So look, at the sort of mentioned there that we talk about our program grant, which is on reimagining engineering design. It's a really large scale initiative, and it cuts across a number of partners. And I'll give you an idea of the scale and scope of it before we go into what the actual research work is about and where we're at now. And it's a culmination of efforts that have been going across the partner institutions in slightly different areas over a period of years, which is formed now into this to try and tackle a significant problem and trying to really just rethink how we're doing design. So I'll give you an idea just first of the size and shape of the project. It's a 5-year program. The full cost is about 11 million. It cuts across 3 institutions. There's ourselves in Belfast, York, and Loughborough. And we've got a super set of company partners, that includes Airbus and Rolls and Glen Timplex, who you maybe don't know so much about it, but they make 95% of the electric heating in the UK, and they own Morphy Richards and a number of other Belling, number of other household names. And of course, we've also got medical device suppliers in Oxnet, and we've FAR UK, who are an automotive company. So a really good range of partners. The core grant from EPSRC is 7.3 million across the partnership. And of course, they are all putting additional support in as well. So it's a really large-scale collaborative effort that brings us across the UK, and a necessary thing, as you'll see when you start to look at the scale and scope of it. We're covering a range of sectors from aerospace, right down to medical devices and white goods. Now, why that's interesting in particular, and you'll be in similar boats, the application areas of design processes are really very different. And large-scale OEMs in the aerospace industry have very different, approaches and needs to those that are dealing with bespoke devices at much smaller scale. So the challenge for us is trying to find better processes to enable innovation. And in terms of a core problem, maybe try and give you a different perspective where it is. When we have we make something, which is what this is fundamentally about in the manufacturing domain, what you see physically is really only the very tip of the iceberg. So we might have a beam, it could be wood capped with steel or an I-beam. That physical shape is actually determined by a number of things that are not necessarily visible to us. So we have what we see in 3D, but in addition, we've got as many other dimensions to the problem as as is necessary for any given application. So material, process you use. And it's really a nice way of trying to express your form follows function, or the function influences the form that you see. And part of the challenge is that often the focus is very much on that, and there are separate activities and processes that deal with the other issues. And that really is part of the challenge in this. And how we deal with it, I've used the example here of an airplane. It's not an uncommon approach regardless of the product. You might have a specification up here in the top right. We have a skeletal type framework representation, and we gradually add detail until you get down to something that you can make. So we're breaking the problem down either by function or by physical representation. And that's very much about getting down to something which is an attractable form. So we do typically try to aim for, one part, one job, right? One component, one function. And when we can solve a local problem, we then build that up again, and we do a reassembly of the whole artifact until you end up with the product you hope. So the Lego bicycle motorbike emerges from the assemblage of all of the individual components. And we've become very fixed with that. That has helped us deal with really challenging problems, but it comes with its own baggage and own issues now. And what it really helps us do is to manage the data and understand the relationship. So as you break down the problem, you know that you're working in a constrained and tractable area that allows you to get another little component done. And it's that managing that level of detail as you go down through the subsystems that you're dealing with that allows you to get some understanding of what's actually happening. And part of that does help you deal with a challenge we have in general, pardon me, of maintaining the design intent. And if you think of a simple example here of a stiffened plate, and if that plate is made with a subtractive process, where it's machined out, we can see that the parameters that are relevant for that across a number of functions in the design and manufacturing process are different than the key geometry parameters that you might look at. For example, if you use an additive process like welding, where you're building an assembly to make the final form. And we did some studies in this, and if you use different parameters to do the simulation and the optimization, and you include the process parameters and so on, then you get different weight solutions and slightly different geometry emerging. It still looks kind of like a stiffened plate, but the actual values of these thicknesses, pockets or whatever are all slightly different. And that's a really difficult thing for us, because you're now saying that at the back end, you have different choices, but up front, your function is maybe quite simple. And it starts to lead to different pathways through the design development. And it's really because the process is sequential, and the way we term it is information leaks away. This is not a complete picture, but gives an idea. So you look at as many concepts as you can, but it's difficult to capture all of the customer needs in the concepts. And so it means that you're starting to add constraints and make decisions. And similarly, then when you go to model and understand the concepts you have, you further do a little bit of restriction. You don't then physically test or make all of these, but you sample bits that help you again understand more of what you're going. You then take your concepts and prototypes and you take that through into your wider organization to build the whole enterprise. Of course, then you start to implement the processes and the product emerges. So there is a gradual shrinking, and it gets more complicated than that, because overlayered are regulations, particularly if you enter very safety conscious industries like aerospace, were equally safety conscious, but also highly regulated in the medical device industry. One makes a few very large scale complex product. The other makes bespoke, individualized products that are equally complex in their own way. So it's a difficult process to manage and to understand where you're going through. I love this diagram. I keep saying this came from our colleagues in Loughborough. They made an ontology map for a single component. And this knowledge that we're talking about and mapping the data, this captures the data flows, and you can see the explosion of paint on the right-hand side is all of the connections and nodes in the data being used. It's a single thing. So it really brings across the complexity involved in dealing with any of these issues. Now, it gets even worse. You take that single component, you take what we've just spoken about, and you start to think about the wider system, where that wider system involves factories, funders, process people, and so on. Energy supply companies, and other manufacturing organizations, and you start to get that contribution into this, and we can see that some of them will have particular functions and preferences, and we, the people, the customers, do have preferences that go into that. If they like, to make square columns in this case, to keep it very simple, but the customers like round shapes, then you start to have conflicts. And that's an easy thing to resolve, but it's a simplistic view of what happens right across the system. You then start to get competition in there, and different organizations and different customer requirements, and you get lots and lots of objectives, and of course they are conflicting. And it's the management of that and how that flows through to help you make the right decisions, both as a design and the manufacturing system. And this is a simple indication of the manufacturing system and the product. We all know are intimately tied together, but how we enact that in practice tends to be quite separate. Not always, but often, and we don't have a tight systemic approach that allows those two things to do it. If the blue square profile dominates, then you find that that's the factory that survives, that's the capability that survives, and of course things then evolve over the years. So if you need to make round ones, all of a sudden you don't have that capability. Of course, you start to add geographic difficulties onto that. That adds complexity. There's logistics and timing involved. And of course, this is now a global operations, and we saw lots of interruptions in supply chains over the last year. So we're addressing that. We've encapsulated as 4 research challenges. We call them, our interoperability challenge, the cyber world, physical world, the social world. I'll take you through each of those briefly and then show you where we are at the minute. Really, the interoperability is for us about the design approach. It's a slightly different view of interoperability is typically being tackled at the minute. So we're trying to interface between different simulation approaches or models. We're trying to bring that back to what you're actually designing and how you go about that process and where you capture and store that information. Of course, you then go from design through to how do you actually capture that in the modeling world and in the cyber world. So appropriate levels of idealization, appropriate transmission of data, getting the right data at the right time to make the right decision. And then, of course, how we take that through to reality and in the process of creating and verifying and validating your physical representation of what you've designed. And lastly, thinking about how that works across a whole enterprise. It's a very wide-ranging and sweeping challenge, and it really is about rethinking the design rules and processes. and about the roles and activities in the manufacturing organization. The reason it's so broad is really at its core, recognizing that we have tended to solve many of these problems piecemeal. And we recognize that we really need to see how they all fit together, because there's probably a different solution in there to some of this. And our approach has been about taking inspiration from nature to try and address this. So it's very much about, think physically as talk about this, you capture all the information, the seed, if you look around you in plants, is all the information that's needed to create the plant, which is the emerging artifact. In organisms, it's slightly more complex. When you have a fertilized egg, one of the really interesting things for me that comes out of these approaches is that the cells initially just divide until you've got a bunch of cells. It's about 10,000, but nothing is functionalized at that point. And it's only at that, once you start to hit certain triggers in mass or weight, and the neighboring cells start to do things, once they've been triggered to trigger other things, and that's where functions emerge in the cell. Now, if you think of that, our breakdown approach of the traditional systems engineering approach to design and manufacture is identifying your functions at the start, and your part of your breakdown is by function to ensure that you're meeting the requirements of the customer. So this is a different way of thinking, and really triggers when would I bring something on board. Now, what that allows natural systems to do, in the end, this is coded up as what we call a genotype. So your genes have the fundamental characteristics captured there. They go through a development process, which is growing, but it's more than growth. There's other things that happen in that, in the functionality and so on. And these core genes actually merge for a really wide range of what are called phenotypes, or the type of object coming out at the other end. And I love the statistics, like a typical fruit like a strawberry is about 50% of the genes that we have as humans. So we're either 50% strawberry or banana, whichever your favorite fruit. But the variety that emerges is the interesting thing. And those small perturbations, if you take them over many generations, it allows selection to occur in whatever form that may happen. And you go around the loop many times, so you get a continual evolution and change of this. And again, we're not implying here that we all become robots or whatever, but it's just to indicate that change over many generations. So what we've done is picked up on that kind of system. It's obviously a bit more detailed than that, but our approach within this and what we've been working on so far has a digital equivalent of the genes, or representation, which is a text with the characteristics we want to see expressed, captured. They are gathered together and embedded in a seed, and that seed then goes through a development process. And just as the seedling would appear to be an organism, we create geometry inside the CAD system and carry out simulations and so on, so we understand and influence that development process. So it allows us to get an artifact from the CAD world emerging. Now, it gets very interesting very quickly. If we just see here on the right-hand side, natural systems, because of that very detailed characteristic level and the process that it goes through, perturbs very easily into different forms. As you can see on the right, the target to hit from the green dot to the two yellow dots, we get a snaky type structure. Our typical engineering approach to that would be to join the dots to make sure the forces or flows or whatever attach and go through those. So you very quickly get into an innovative domain where you get lots of solutions emerging, and we can grow things and we add little buds and structures, and you get things then looking really quite different, but still fundamentally satisfying the basic requirements of making sure we connect the 2 points. Some of these you wouldn't do. Some of them are interesting for different areas. So that's the overall concept. If we go in then to think about each of the 4 key threads, as we call them, because they're all interwoven and interdependent. The first one, in terms of how we do that design process to ensure interoperability. Again, this is a nicely captured diagram. It's really busy, but if you just look at the overall picture, on the left-hand side, we're trying to express here the plethora of simulation models and computational approaches we have to help us understand. They range from FE, CFD, through to cost models that are spreadsheet based, for example. Of course, we need to test elements of this down at the bottom left and figure out how to assemble things together. And all of this flows through to the right-hand side. And you see here in the middle, we're trying to ultimately get a solution engine that helps us. You look at the top right-hand diagram, that helps us understand the characteristics that we as the end users of the artifact that's emerging, the product, we understand where it has come from, why, so we can address its quality, how quickly we need it, how long it needs to last, sustainability and so on. But very importantly, that we capture the train of decisions that led to the form of the emerging product to be the way it is. And that in itself is a really big challenge. So, you can see if you start to pick that up from the approach that we have, where we're trying to build that. Now, when you even build this, what becomes really quite interesting, I'll show you these 2 things, just let the animation grow quickly. You can see that as that has grown and developed, that it's much narrower at the top than it is at the bottom. And that's natural systems grow like that. And if we reflect this in engineering terms, it means that as you explore the design space and your design evolves and develops, then the simulation is informing you, how much material you should have at any point and how this grows. So you even get to this point whereby you're reflecting that, but it's a complicated model. And all of that needs to come together with the simulation. And that means that your geometry is changing, your boundary conditions are changing, your loads are changing, and all of that needs to be reflected at every growth step. The nice thing is that if we get that right, and this is an image from one genome, one genotype that comes out, and it gets expressed in the environment in all of these different ways. So you can see the range of solutions, some of which, as I say, are completely crazy, some of which are nice and simple. You can see a little angled bar in here. Here's a little, stiffened ladder structure, which is what we were aiming. There's another variation of it. That's the kind of thing the problem was set up to do, but it produces all of these alternatives for us. So it's really pretty a decent opportunity to introduce innovation to the system. Now, that's the natural bit of it, and we're looking at that, but we are exploring alternative algorithms. Here's one just using a more standard genetic algorithm and approach to produce populations and generations for a bridge type structure where we're growing little lattice networks, connecting them up, looking at the forces and seeing how that emerges. So we're trying to keep a little bit of a balance. Where this also becomes very challenging for us is back to that wider network system where we are thinking about, our customers, the people involved in the organization, the manufacturing organization, and it's how do each one of those influence it. So we have a tendency to think in the height, weight, where it is, what size it is, the cost of it. But the expression of these either objectives or constraints, and how they then influence and emerge as a purple bit of the column or a green bit of the column, round or square, then that's part of the challenge as to how we get that going. So that's in principle the real crux of what we're aspiring to do. How you model that becomes very interesting. This is a nice simple example of you see here the Z-shaped stiffener. This is a common airframe type structure. We have a piece of folded metal or extruded, which is going into the page, and it's connected to the frames, which are of course run the other way. So the person who makes that's thinking very much about that type of real physical form. But of course, the stress analysts who are trying to figure out what to do this and what size it should be and so on, will often think in a much more abstract form in cross-sectional areas in moment of inertia and so on. So we have a nice simple example of the different forms needed, and it's really about getting the right representation to support the right decision at the right time. This is a component at the back end. It's called the tail bearing housing. It's at the back end of an aircraft engine. And we've got some simple models that are just simple, line representations through the shells and solids. And indeed here in the bottom left-hand corner is a mixed dimensional model with some shells, some solids, and some beams. Try and get a rapid solution to help make the design decisions. And that representation, again, that's part of the challenge, is how do we get the right representation of whatever you're producing? And it leads you to think about, what you're trying to support. So we might have nice abstract models like here on the left-hand side, but they ultimately have to be represented in some form that you can then transmit the information to the right part of the manufacturing organization to enable it to do its job. I like this as an example because it challenges many of the even existing nature-inspired solutions. You see lots of stuff to do with, for example, mold growth and so on. And it's easy to get, these kind of pictorial images that are useful and they trigger ideas and they can give you good concepts. But when you make the solid of that on the right-hand side, when you put the real geometry on, all of a sudden the junctions and joints that you see become very important. And the detail of that in a simulation environment and then consequently a manufacturing environment becomes very different. And that will impact on the kind of stuff that your network is interested in tolerancing, in terms of coatings or surface finishes. Here's a very simple example of just one of these branching structures. And the meshing solution in around this joint is non-trivial. So it's nice to have the nice 2D image that maybe triggers you to lead something like this, but you have to have in the background the tools and capability to represent that appropriately to get the right and reliable solution out. And that leads us back, of course, to when you put those simulation models on and you start to grow structures with stress or with temperature or with fluids around it, then this whole thing becomes dynamic and changeable. So the data structures, the data trees, how you store the data, all becomes really challenging. In the physical world, we start to say, we talked about having the right representation for manufacturing there. If I go back then, just from that simulation type perspective, and then take you over to the right-hand side here, where the organization or team that has to produce the real geometry of this that connects into the rest of the system or is sold on, up the supply chain, has to think of the geometry in a much greater detail, and the properties, of course, as well. So the representation needed here is really very different than the representation needed here. So, what's the process for getting you through to this point is a very interesting challenge also. And that leads you into thinking about verification and validation, where there's a traditional V diagram from systems engineering. We have our definition from concept going down. So say we break the problem down, you're building back up through your integration and test, and you are verifying and validating as far as possible at every point along the way. But that's necessarily only at key checkpoints. And when you start to do this for different products, particularly if you're going to more bespoke situations, that kind of approach starts to break down because you lose efficiencies, there's too much variability, and it becomes very complex. And it can be seen here on the right-hand side. Again, it's another diagram that I both love and hate. It has, it's really fantastic. It's a scaffold, very interesting. It's part of a bespoke medical solution, but it's horrendously complicated when you start to work out the validation route for a product variation in that environment that's supplemented then by actually very heavy regulation at the back end of it. And how you then get a design change through and understand how that design change is happening in this constraint is horrendously difficult. The properties that you're trying to extract from these scaffolds, and how they perturb based on the perturbations of the underlying characteristics is very much a non-trivial problem. And in terms of that, we talked about bespoke there. We begin to then think about people not just as the end users of this or the end point of it, but how we all are part of that system. And humans appear in this loop, as end users, but yes, there are also people who enter data, people who cut things, who assemble things, who plan it out. We are the solution to these things as well. And humans, unfortunately, there's a lot of work going on at the minute where it's about taking humans out of the loop. And we have work consequently going on about how we integrate humans into this, like cobots and so on, and cooperative systems. But you see a lot of this kind of diagram where, automation shows you high confidence and we can put rules and constraints around it. We don't have much confidence because humans are the source of some problems, but they're also the source of many solutions. We are the ones coming up with the concepts and innovations. So one of the things we're interested in is how we understand when are humans part of the loop with high confidence that they're really adding value to the process, and when do you need automated systems that do that. And that comes back in what kind of system you're designing and how does that play into the whole organization. And this is really interesting when you talk to industrial practitioners and you think about this. So we're moving towards thinking about this across the whole enterprise to make a complex product. It does sometimes come down to individual decisions. So it's how an individual actor in this system makes a design decision or influence a design decision. Simple things like, people are paid by piecework. So in some instances, so therefore, making another 10 of whatever their widget is that day gets them a little bit more in their pocket. Do they necessarily pay the attention that maybe another part of the system would like them to in that? Well, they're not asked to do that, they're just asked to do that one thing. Of course, then that same thing happens at company level, where you maybe have a perfectly really good and valid product line. The company has other product lines that are in trouble, overall profitability changes, or there are different legislation factors emerging where decisions are then made to impact that. And that can be then difficult to incorporate into the system and to make changes. So we get those, and then of course that easily layers up to think about global effects. We're still in the middle of something that is demonstrating that very clearly, but that also occurs in life outside of our current position, where exchange rates fluctuate, companies go, inflation goes rampant, or companies go out of bust because of legislation in a different country, all kinds of things, and the impact back up the supply chain. What's interesting from that, from a design perspective, is do you then try to get exactly the thing that you had made there, or would you have maybe modified and tweaked the design slightly in different parts to accommodate a variation that might fit in it, but still provide function and all of the other bits of traceability, satisfying regulatory issues, and so on as well. Interesting domain. And I'm just going to quickly run through this. I don't dwell on it too much because I want to show you some of the current work too. But we've run this approach in more practical terms, using the example of a plastic storage tank to try and see, can we reduce material usage and see what happens to it over a number of generations. And we picked a few design characteristics. We looked at the manufacturing process, what happens when material gathers in corners, becomes slightly heavier, and so on. We get stress concentrations as a consequence. And the study in allowing this to vary the geometry so that you have a better process and running it over a number of generations produces lots of interesting results. Here we're running through picking out where are the thin regions, where are the thick regions, where we're getting our loads on. And that shows, a tank in many variations here. The point of this is not to say which is a solution, other than you get lots of variation quickly to allow you to understand the problem in a better form. So where are we now? The sorts of things we're doing is trying to understand how that environment that's wider impacts on the geometry. And at the minute, it's a simple position. Once we crack this, we'll be able to start to explore how that happens for people, factories, and different practices, of course. So we can locate things in space. We can give them an impact or a potential thing, potential impact on the design, and we can use a simple radial basis function to indicate both the field and the response to that. The way we do it is we pick, if it will come up now, we put what we call receptors. A little sensor sits all over the geometry that you're building. The sensors themselves, you'll see, will read whatever that environmental input is. It assesses its strength. It then creates a response internally in the organization, or organism, as we call it, or artifact. We use a hormone analogy, and that impact is then converted to an effect on the geometry. You'll see there the vertices lighting up. And the consequence then is that those 4 points will move in response to that. We can do the same thing for an internal condition like a stress or a strain. We model those properties in the genome, and we do the same thing by having a sensor that says, detects what the localized stress is. We're actually using a strain energy density function here. That triggers something in the response of the sensor, which we can then convert again into a geometry response to that, so that we will either reduce or increase stresses or for the next iteration. The result of that is that the cube up here on the right, will maybe have started off like the solid block, but as it grows in length and as you measure the stress, it will also change its geometry automatically in response to that. So it's creating really a developmental growth cycle. Kind of things we've been able to do with it, simple shelf bracket. So we're not quite at airplane level or anything wildly complex just yet. But we can put simple conditions in the main loading beam here with some support struts attached to the wall, and we were able to grow that and get particular shapes emerging. When we tweak the genotype and we run it through a larger population, we get ranges of interesting shapes. You can see some slightly crazy things here, and part of our job now is to try and understand this mapping between the genotype and phenotype, so the genes and the final shape, to see that we get similar things, possibly like the top right one here, that's maybe more like our existing types of things we expect, or maybe something like the second one here that is a little bit more ornate and has a nice feature. So there may be things that can come out of it that would trigger different potential solutions. So it's a really challenging problem. One of the things we're now trying to do that's possibly relevant to yourselves or thinking about that is, there's going back to thinking about the stress and strain sensor. That equally applies to either surface finish conditions or coatings, where you can adjust the geometry necessary. That's large and chunky. Obviously, if it was a layer of paint, it would be just a very tiny change on it. But where that might be interesting, what we're keen to explore as part of this, is when you come to do joints and so on, how do tolerances stack up and how do they change as you're changing the design? And would that then result in possibly different configurations or different locations of branches and joints that might fulfill the same function, but be more tailored to what the final product will be like, rather than this additive and separate process we are already too constrained. And we've played with this already to do. It's dead easy for us to add little very small blends in the red here, or big chunky chamfers here that we put on just to make it look very visible. And I'm showing you this because I like it, because it highlights both the interest and the difficulty in doing this. If you're used to using CAD systems in the geometry world, you'll see some of this is easy. If you're not, it's really not obvious. The blend you'll see in the middle here that blends the rightmost cube and the bottom left-hand one is, if you put that in a real saw, you have to chase those the whole way around the object to tie it up. And when you have them all meeting, it becomes a very difficult geometry problem, which impacts on your boundary conditions and your simulations and so on. So that's where we're at. We've got some interesting concepts. We've got some real engineering problems under that to try and solve, and maybe tweak some interest to you. It maybe just even maybe, I hope, just fired off some ideas that possibly you can use. Interesting times. I do want to thank my team as a roundup. This is a mixture of the academics and researchers, and this is all of us so far. And we're growing again this year with new recruits coming on over the summer, and we have new PhD students starting in September. And yeah, just always remember, imagination is our only weapon in the war against reality. And that's me. Thank you very much.
Thank you so very much, Mark. That was splendid and well-timed and well rehearsed and presented as well. Let me first invite people if they would like to ask any questions. Alternatively, I mean, if anybody has any questions, you can also email Pamela, and then we can collect thoughts of Mark later on and get back to you anytime.
So I don't know whether I'll bore you all or
No,
stop.
it was so well explained, Mark. It was nothing. I have one question, Mark. So, when you showed this line diagrams when they are connecting, what was the basis with which they were put together, or was just an illustration?
No, so that's those lines are we keep a range of geometric representations in the software. So that those 2D line representations are just the connections of the centroid of the end faces of the little blocks as they grow. So all you're seeing there are as the endpoints, and then the 3D representation is obviously when you apply the cross-sectional shape of that being whatever it is, square, triangle, pentagon, whatever eye shape. That's why it's important to have the 3D representation.
Right. And in terms of the science, I mean, if we go by the traditional physics approach, Mark, then one of the agreed rule we always go to is the minimum energy path. Uh, has there been any thought process around that, like to take some of these scientific facts into informing the design evolution?
So we have looked very briefly at minimum strain energy solutions. At the minute, we're not so much concerned with actually optimizing a solution, so much as getting a range of innovative solutions, which you may then further tailor or optimize if they're good or interesting. So we've done that. We have also played with, which I think is interesting, is an energy budget. And the driver for growth there, as we saw it, is being driven by trying to reach a certain goal or length or touch a number of objects. But we have put that in as the growth driver is the amount of energy you have, of strain energy. And as you put that energy in, it converts to strain energy in the object. Then, you deplete your store. And that was very interesting because when you run out of energy, you stop. So it does allow you to say, I think this is the physical limit, and therefore these would be the shapes. So that was very interesting, and that will definitely play in again. It'll be probably towards the start of year 2 that we're looking at some of those, front end drivers to give us different limitations.
Fantastic. I feel like I'm only asking questions, so invite people other than me.
Like it's lunchtime and it's the end of the year. And I mean, as I said, I hope it maybe piqued your interest in that. If happy for people to ping me, but don't worry if there's no.
One more question, Mark, out of curiosity. You mentioned although about resilience in the design. There was recently also a lot of buzz about responsiveness. Is that also an element associated with it, or?
So yes, and responsiveness comes in a number of ways. Sort of so we've in the precursor to this, we did some experiments over the cloud through Raspberry Pis to 3D printers. Just feeding back simple information like, material left, bed size, status, on. And the principle behind that was to see could the design change if a printer goes offline, for example, would you then adjust something as a consequence, and you can demonstrate that. Where that becomes, I think, really interesting and really hard is if you have higher frequency processes, whereby that's, I just cannot picture how you would do that on a machining process that's midway. But it might be possible at steps, through it that you would adjust things. But I think those are very important. And the larger scale element of that, again, is the supply chain. So you do want to be responsive to that. And it depends again on your process and the time scale to produce. So if a supplier drops out of line, have you a system that immediately pulls another one online? Or do you just simply tweak your core design and say that article 514 coming off the end of the line is now brass rather than whatever, right? Or it's this size rather. But I think that's all possible. And what we're trying to do is to see, can we combine a lot of those?
Sure. There's one question from one audience, Mark, which is about how can surface engineering make a contribution to your project?
So that's a good question. We would be really very interested in understanding aspects of the, where and when particular processes occur, typically, and then what is the impact of those processes typically on the article that you're making, either in the tolerancing, for example, so what's it doing to the geometry, and also are there, in surface engineering, well, I was going to say it doesn't really change, it won't change typically maybe the physical properties much, but it is going to change properties potentially. And we're interested in all of those changes. So anything that you're doing that's affecting a change on the article being made, really interested to have examples. If there were simple examples or challenges, that'll be good, so we can start to play and get a handle. But I think it's something could be very useful for us. We start to even take, machining and then how we're making in some other materials. There's now lots of fitted joints rather than, bolting and bonding and so on. And particularly in the plastics world, I don't know how much you work in that world. But all of those things impact the design and the shape. And so anything you're doing that's influencing that would be really interested in, really.
Sure. If there are any other final question, otherwise I'll like to invite Professor Alan Matthews to give a word of thanks, Mark. This was really, really wonderful, not only to catch up and to hear and exciting ideas and program going ahead.
Thank you.
Yes, thank you very much, Mark. Fascinating to look at how design developments are progressing now. I mean, there are so many questions. I didn't like to ask one simple one, but I mean, very often a company will find a design fault and will address that particular fault and might not address other less dangerous faults. And I think your approach allows you to take a more balanced approach to, we all know of, for example, cars that got a reputation for rusting. So they'll just address the rusting problem and not address something else. I think there are lots of examples like this, thinking of something that can be addressed by surface engineering. So hopefully your approach enables a more across the spectrum of design characteristics to be addressed. But what I still don't understand, Mark, and this is the $64,000 question, is that we all know as the human body will develop, if it has a weakness, it will build muscle in a certain area, for example. But I still don't know how it works that when from one living item to another, how does nature converse, or transfer the requirements to the next, the next body, so to speak.
Yeah,
I guess it's all in the DNA somehow.
Yeah, they copy it, and it's really a case of that organisms that had the ability to respond are the ones that perform better, and so consequently they survive. And all they do is make copies of themselves. It's an interesting aspect of this that we find when he started to dig in is it's about local response and local decisions. And the individual cells, and they don't know what they're doing. They just do it.
Okay.
And it's and they make blind copies. So when it works and gets passed on, if it perturbs through mutation or through crossovers in genes,
Yeah.
if it doesn't work, that just disappears. So it's a very wasteful process. It's not an efficient way. And that, I think, is one of the challenges for us, is to understand exactly what you've said, is, you know, how does that's a good response. How do we capture that and encode it so that it's copied faithfully into the next generation and then appears when it's useful, you know?
Yeah. But, you know, so it's a kind of survival of the fittest kind of aspect. But of course, you don't get something dying off because it didn't work. And, you know, you can fully appreciate that's part of the model. But still, you know, as evolution carries on, we adopt certain features, which are matched to the environmental needs.
Yeah.
And it's not clear to me how nature does that.
Yeah. Oh no, and it's not, it's not really clear to many, you know, people in biological systems. Well, they obviously know an awful lot more than me, but when you read papers, there are things that they make very clear statements that they do not yet understand. So with our little hormone idea about changing the geometry, so the idea there is that we can pull, you know, a stress, a temperature type response, and through a hormone just aggregate it into a single geometry change. Mm-hmm. And that comes from plants that do this by a hormone called auxin. But, you know, I read a paper recently, by Ottolina Laser, as it happens, from like a few years ago. It's a very simple paper, but it's a very clear statement saying we do not fully understand.
The time is 2 p.m. Right now in Manchester, it's 21 degrees and mostly cloudy. Today, it'll be mostly cloudy.
I think that's coming on Pamela's.
Yeah. And they're quite clearly saying that they understand elements of what auxin does as a hormone, but they don't fully understand it. And all we're trying to do is steal those little nuggets to do it.
Yeah.
I do think there's a really nice thing if we get this right, is that what we might find, what we're hoping to find, I guess, is that we also have genomes for the manufacturing processes. Then what you could find is that good combinations of product and process emerge, so that both of them come together, rather than what we do at the minute is, I can bend metal, so I bend it. I can sand, so I sand, but I can't shot blast, or I can't paint, or whatever. And that could be a really interesting domain, certainly from the design exercise.
Yeah, no, it's definitely the future, Mark. Yeah, absolutely, and great work for getting the team together and addressing this important challenge.
Thank you.
Thanks very much again.
Okay, thank you. Thanks for having me. Bye.
Bye.